Bonsoir. So I think we will begin. Thank you for you to come. Such late presentation. So my name is Elsa BALLINI. I am a professor associate at Institut Agro in Montpellier, south of France. And it's an old agricultural university, 200-year-old university. And so I think at each ICPP meeting there are some teaching sessions, and each time we try to make some connection between teachers. And so we will try, like the other. So I've created this QR code that you can scan, and you should arrive at a form. And the idea is that you can fill the form so that if you have any initiatives that you have past initiative, or we may be interested in future initiatives that you would have on pedagogy, on plant pathology. It can be some, I know that some people would like to do some serious game about plant immune system, or any initiative you have, you can share it on the form, and I will try to send all these results to the people that are interested in that. And maybe we can connect together as teachers in plant pathology. So you can fill it during the session or after the session. And you can also share the link to your friends. And that's one initiative. We'll see if we have something. You can present you.
Yes, thank you, and good afternoon, or good evening maybe, even. My name is Erik ALEXANDERSSON, and I'm from the Swedish University of Agricultural Sciences. I am, like Elsa, an associate professor there, so not primarily a teacher, but as many researchers, we also need to engage with students and teach. And I've done so at the master's level quite a bit. In our background as well, we are engaged in something that's called ELSE, Euro League for Life Science, which is an initiative among several life science universities in Europe, trying to lift master student education and also on early level PhD education. And this year we tried something new. We tried a competition, a plant health, grand challenges in plant health, we call it. I think we have one of the winner here. There, Mila, is Usama here as well? So actually the winning, you wanted to point out, the winning students, at least one is here. Extra point for you, Jamila. They won an entrance here, ticket and travel and accommodation to visit this conference. So, does the QR code work for you? Yes. Great. You can also, to get it interactive, use the app. So if you have some type of teaching or outreach related initiative that you want to post there, we're going to post the ELSE link, for example. Fascination of Plants Day is another initiative that we've been engaged in that is important. Those type of initiatives and teaching materials that are publicly available, please post them there as well, and then just be a little bit clear when you have questions for the teachers. Or for this, not the teachers, for the speakers. But since not everything is electronic, and we are actually, Elsa, you're saying all the time that there will be no one in the room at this time. It's almost full, it's great. We do some non-electronic tests here as well. So could everyone that is a teacher in some way raise their hands? Okay. Oh, more than half. Very, very good. Researchers. I mean, you can be both teacher and researcher. It's fine. Even more researchers then. So, communicators. We have some, yeah, good. Some are all three, that's great. And finally, do we have any students? Oh, 3, 4. Oh, that's good. Okay. Thanks. Then we know. Very good. So with that, I would like to introduce the first speaker. We have Maria GULLINO here, who's going to, according to your abstract, give us a little bit of background on how teaching in plant pathology has evolved and changed during the years. 2 plus for many years. Oh, really?
Good afternoon. I'm glad that the meeting is ending. This is my finally my last talk of the meeting.
Yeah,
So many. I will take you through a journey because, as you can understand, I would say I did accumulate some experience in teaching, starting in the very early 80s, teaching in a relatively small country, which is Italy, and I will go through the different geological eras, I call 80 2000. Then the first 20 years in the 2000, then we have the COVID period, which is a very peculiar one, and then after COVID, with some consideration and looking ahead. In all this period, we have 3 important elements: students, teachers, and the environment where we are teaching and working. So I will try to focus on how these 3 elements did change, at least from my perspective as a teacher. And we know that they changed a lot during the past 40 years. And especially we will see after the 2000 and with COVID, we had really a disruption in the way of not only teaching the tools that we had to apply, but also in the way agriculture, I believe, is seen in perspectives. So if we look at the students, in the 80, 2000, of course, I repeat, I am providing my perspective teaching in my country, Italy. We had very few students motivated, mostly coming from technical schools at the time. So they knew agriculture. Very few were coming from classical study like Lyceum. It was almost mandatory, the attendance. So anyway, students who attended classes, who attended the practical courses. They used books to study. They were motivated. And we had plenty of practical activities because there were few. Then if we go from 2000 to 2020, we had plenty of students, many students, sometimes also too many students, coming from all kind of courses, so not only secondary school, not only from technical schools, but also from Lyceum, from classical studies. Many were, of them were motivated, but also many of them were attracted, they had a kind of attraction, they were considering agriculture in a very romantic way. So they were more attracted by nature than by real agriculture. They were still using books, but started using also other tools and slides and so on. The attendance started to be reduced also because there were so many and we did not have so much space. So in some cases we were also tolerating the fact that they were not attending so much. With a limited knowledge of English, this is a characteristic that unfortunately continues. And we had to reduce practical activities in comparison with the past because there were so many that we started dividing the students in groups. After 2020, students started reducing. The background is always very variable, and generally they have a very low basic knowledge. Generally they have a low basic knowledge also in the language, in many things, unfortunately. We have very much reduced attendance of classes. They are on the English, they know English maybe a little bit better. They know how to use digital tools, so they are good in this kind of thing. They don't use books anymore. They, unfortunately, they study on slides, which is absolutely not a good system because you can immediately understand that they don't put the things together. And the practical activities are again limited because anyway they are less, but they are still many. I'm not saying too many, but because it's not politically correct, but there are too many in comparison with the infrastructure that we have. Teachers. 1980-2000, teachers generally had a lot of experience, broad experience, and a lot of practical experience. Most of the teachers in agriculture knew agriculture, so they knew what they were teaching, they knew what the students were needing. They didn't probably sometimes know English very well, At that time, we had many specialized courses, so going in depth, diseases of vegetable, disease of ornamental, disease of cereals, and so on, physiological plant pathology, so many very specialized courses, very few courses in English. And teachers had experience. Before teaching classes, full classes, at the time we were teaching practical courses. At least, for instance, I started my teaching career by teaching the practical part of the course of my professor. So I was learning how to teach, and then I was passing to teach full courses. 2020, it started decreasing the knowledge of real agriculture among teachers. Some of them come from other fields like biotechnology and so on, so they have not so much knowledge of what agriculture is. There is also a tendency to start teaching full courses very early in the career, because professors are passing on the task of teaching. So, and teaching too early means not only not having a lot of experience, but also taking away time from research. So starting teaching too much, too early, I would say. Better knowledge of English. A still limited ability to adopt new tools, because in this period there were new people, but also older people. And high specialization, in the sense that very often they came from a very specialized field and they don't have a broad experience. After 2020, more and more limited knowledge of agriculture, taught teaching agriculture, very little background in agricultural studies, often very limited experience in teaching. Now they hire you as a not even permanent researcher, and they put you to teach. So sometimes they say poor students, sometimes. And, but they are more adapted to the use of new tools. Environment. In the 80s, 2000, agriculture didn't have such a high consideration, in the sense that it was not considered so important, especially agriculture, the productive agriculture. So there was a lack of literacy in the public among agriculture, and many people thought that food was just grown in the grocery. So it was really a very poor knowledge. 2020, maybe agriculture is more known, but again, the romantic part of agriculture, what I call, again, I say something politically not so correct, the slow food attitude became prevalent. So only one part of agriculture was considered, instead of considering also the real productive part of agriculture. There was a very negative attitude towards GMOs, towards pesticides, and farmers were still seen as polluting the earth, instead of considering farming like something helping earth and the planet. And the general public was ignoring innovation, that agriculture is based on innovation, most of the public. After 2020, I must say, thanks to COVID, agriculture got much more attention. People understood that if we don't produce food, we don't survive. And we see more openness to innovation. And the climate crisis also is helping putting attention to agriculture. And of course, all of these aspects have an impact on the teaching in general, because we are teaching in a certain environment. Teaching methods for many years didn't change so much. We have been very traditional in teaching mostly in the same way, with frontal, we say, classes, explaining to students with not enough practical teaching. Internet permitted easy access to more data, so students started being able to find themselves material, and professors, teachers were helping them to find more material. During the time, there was a shift to use new tools also useful for a long life program. COVID caused a strong disruption, as we all know, because most of us are teachers, so we knew from one day to the next one we had to change completely our way of teaching. This was our campus during COVID, and we were lucky because having a lot of space, we could anyway, as a researcher, go to the campus to work, but the students were not allowed to come. This is an example of the first graduation done online. We were home, students were home. When I did my graduation, I was very excited to how do we say, with the students, when you have to tell you in name of the law you are becoming, and so everybody where I'm living came out from their windows and to see what was going on. And this was also the way we were working. This was an upper part, and this was the lower part of ourselves. Very often, we must admit. We had cases, interesting cases of sisters. Only one was giving the exam, also for the others, but we could discover, because the entomologists, they are very much precise, and they could discover from a small nail on the face that it was the same person always acting for us for the other. So we had interesting stories during COVID. We very quickly were adapted to new tools. First, we did register the classes, then we were going online with the students, and we also started using new tools. For instance, the podcasts that we were producing for other activities were also used to provide students with material more interesting to listen. We were acting directly with the students in the second phase of COVID, and we were devoting days, hours to discuss with the students. Students understood how to interact, and we were even able to have practical parties, having students in their garden, in their backyard with cases, and we did our best. And of course, in this situation, it was extremely helpful, the material that was provided by APS, that being such a huge society, really is providing so much teaching material that was extremely useful, also the practical classes and so on, helping the students. Because the practical part was the real problem. But we did succeed, and students, I must say, were extremely helpful and proactive in doing practical things. After COVID, of course, now we are using the experience gained, and distance teaching can remain important under certain situations, can permit you to bring foreign professor teachers in your courses at at no cost, basically. We can give courses for technical extension people, but for sure we are back now finally again to a classical teaching with the students in the classroom, with practical activities and so on. So the other aspect is that the pandemic attracted much more attention to agriculture. So now again we have a number of students that want to do this kind of courses because they are attracted not by the romantic part of agriculture, but by the practical, productive part of agriculture, which is the current situation. We are a declining number of qualified applicants for graduate school, but I know that somebody else will talk about graduate school, because we are missing qualified applicants. At the moment, we have a problem of good students, good people going abroad, and we are not indeed finding very good quality for graduate school. We have a declined number of faculty with a broad experience. We have more and more people very much specialized, lab-oriented with little or if not any practical experience, that are forgetting that we, in our courses, we have to prepare graduate in agriculture, not researcher, because you prepare researcher with a PhD, but in the courses we have to prepare people ready to work in agriculture. And this is bad because in some of the courses taught at the moment are missing parts that are fundamental for the students. Which are the challenges, shortly, because I think the time is almost We must use students to attract the best students. We can work with focus group with the best students. We must invest also in summer program. In the States, they do it. In Italy, they will never do this because in August, everybody is disappearing. It is, if you should see, they've sent me today how is the situation in our lab, in their lab today, empty. So they don't consider having summer courses for attracting students, but because on the contrary, having courses, having activities in summertime, you can attract students. And you should also provide example of topics that are relevant, that are important, food security, food safety, and so on. In student education, we should have more on-farm experience. We should remember that we have to train people working in agriculture, not researcher. We need also to give communication skills because most of our students in our courses, we don't teach also as to communicate to outreach, which will be very useful in the future. And we should also find funds support much better the students with experiential training, with more activities. So also for this we need grants, we need to find money as teachers. We need internship with industry, which are extremely important. We need to bring people from the industry into our courses. We need to invest in critical infrastructure also for teaching, not only for research. We need to use new tools. And fortunately, at least from this aspect, we learned some from the past. We need also to bring critical thinking, to have students more independent. At least in our country, we tend to reproduce ourselves always. But on the contrary, we need to produce students with a much broader breadth of expertise. And we need, again, I repeat this, to avoid to propagate ourselves. We also need to collect data about where our students are ending up after the graduation, where they work, which are their salaries, and so on. We need more information about the industry need in order to focus and to change. We are also very slow in changing the focus of our courses. When it takes so long to start a new course, then when the course starts is already old, and it takes 20 years to understand that nobody matters anymore about this school, because another very negative aspect, at least in my country, now I can really tell this very clearly, is the fact that courses are built on professors and not on the student need. And this should be the big change to do in the future, looking for bright students, bringing new material, new way of teaching, thinking if we're considering circular health, for instance, which I prefer to call circular than One Health because it's more comprehensive. We need also to bring also a new way of teaching, to be much more multidisciplinary, and even in our teaching plant health, if we consider circular health, we have to bring something new in our courses. But especially thinking when you build a course, the course is done for the students, not to make new position for professors. And so I think, and the end is this: put passions in your teaching. Thank you.
So we have time for one or two questions.
So quickly, I'm Natalie Becker from the National History Museum of Paris, and I teach in Reunion Island about agroecology. And I wanted to know the trend you presented that is before 2020 and in the middle and after. Is it specific to a geographic region? Where does the data come from? Or could you give us some details?
As I told at the beginning, all my teaching was done in Italy. So it's in northern Italy, but I took data considering the country in general.
Thank you.
don't think we have, there's one more question there. Yes, and you can also pay.
I'm just wondering whether student fragility is a common phenomenon.
Yes. And we have more and more cases of declared fragilities in different fields after COVID. Yes. Yes. And it is in some slide, yes.
Yes, I saw that. And
Yes.
And I just wonder whether at some stage in this discussion, maybe not now,
No.
cheers, we might have to talk about that. And
Yes. Yes.
That's an important question. Thank you.
So thank you again. Our next speaker is Brett ARENZ, who will present teaching plant pathology in a larger context.
Hello. Okay. Hello. My name is Brett ARENZ, and I'm a teaching associate professor. So this is a teaching-focused position at the University of Minnesota, and it's actually half of my position. The other half of my position is the director of the Plant Disease Clinic on the St. Paul campus. So what I'd like to talk to you about today is a class that I developed at the University of Minnesota called Plague, Famine, and Beer. The subtitle of this class really is How Microbes Have Affected Human History. Okay, and I've tried to think very broadly about this subject, as you'll see. So this is an online course. It didn't start out online, it started out in person, and I was able to sort of develop some of the themes and then turn it online after that. So it's for undergraduates. So I started about 10 years ago. At the University of Minnesota, they have a number of liberal education requirements that undergraduates are required to take before they can graduate. One of them, it's called the core curriculum. One of them is a historical perspectives requirement. So I was able to get this course approved for that requirement, and that's really been one of the main magnets for students, and I've gotten about 100 to 200 students per semester since then. So if we are to be maybe somewhat crass to say class success is gauged by popularity and student attendance, it has been fairly successful. I just want to give you a little bit of a glimpse of one of the kind of subject matters I get into in the class. And you know, the theme of the conference is One Health, so maybe thinking even more broadly about that before I talk about maybe some of the other things the class gets into. So thinking about disease causation, of course, when we think of human disease, two of the individuals we most credit with contributing to our thoughts on this, of course, are Hippocrates and Galen, okay? And they really contributed enormously to concepts of medicine and anatomy and physiology, and even really what it means to be a doctor, developing the career of a doctor and medicine. And they really largely rejected the supernatural as causes of disease, which obviously was a step forward. But that didn't mean they were necessarily right about everything. And of course, one thing that was a struggle for them is the microbial world was unknown to them, totally. And so their ideas of infectious disease really came down to humorism, which is this idea that there was bodily fluids that were in imbalance, and that led to disease, whether it was blood, phlegm, yellow bile, black bile. And that didn't necessarily explain why suddenly a large group of people would suddenly become sick in a small area. So for those kind of diseases, they developed miasmatic theory, which is basically the idea that the air itself was toxic in some way, right? You think of a disease like malaria, bad air, right? Literally named after this idea, okay? So while you could argue that miasmatic theory may have inadvertently led to some advancements in health and sanitation and things like that, you know, the sewer systems, humorism really unfortunately led to things like bloodletting as a treatment, which largely probably did more harm than good. Okay, so let's talk about the plant side of things, okay? Thinking of another luminary here, Theophrastus, termed the father of botany by no less than Carl Linnaeus due to his contributions to plant classification anatomy. author, or at least compiler of Historia Plantarum and De Causis Plantarum. So his approach largely relied on observation and deductive reasoning, okay, to try to describe what he saw. He made some interesting observations in these texts. First of all, that cereals suffered more from rusts than legumes, and that farms in lowlands suffered more disease than the highlands. We could kind of conceptualize now why that might be with the difference in environment there. And also that wild trees suffered less disease than cultivated ones, okay? And we can also sort of understand why that would be, even if he perhaps didn't understand why that was happening. He talked a little bit about plant disease, not a lot, and mostly with causation. The mechanism he came up with was sort of adaptations of humorism or miasmatic theory. Fast forward to the medieval period, really wasn't too much change from the classical. Just pulling out a quote here from Conrad of Megenberg, who was a prolific scholar from this time and a contributor to many primary sources, which are very useful insights into the medieval period. So this quote from the Buch de Nature: "The vapor that creates the mildew is very fine and burned by the sun, which at the same time makes it rise into the air. If this vapor suddenly changes into droplets, it falls upon the crop and will burn the fruitful substance in the same way as hot ashes." So literally thinking that disease came from the air, right? And it was linked closely to the weather, which again, we can understand why that would be, but because the microbial world was unknown to them, they couldn't make that link, obviously. And I should mention too that they use the terms mildew and rust and blast in a really interchangeable way, whereas we have much more sort of specific meanings for those words. Okay, so let's look at control of plant disease. What did they do? Well, of course, everyone has heard of Robigus and the Robigalia. So certainly praying to try to prevent disease would have been, something that was done. One useful group of texts, the Geoponica, which was compiled from the Byzantine from about 700 to 1000 AD, had some interesting recommendations for control. First of all, you could throw laurel into your fields to draw the, again, quote-unquote mildew away from the wheat, so some sort of transfer of disease onto a different substance. You could perhaps treat your seeds with wine, ashes, stale urine, or sort of straining them with a perforated seal skin. And again, some of these are interesting because if you think they might, if you use something that had some sort of antiseptic quality, like maybe a high potency wine, you might actually get some potential improvements there. Fumigation was something that was sometimes recommended, using things like burning straw, crabs, fish, dung, animal horns to fight things like rust. And this is quite clearly linked to miasmatic theory, right? Trying to fight bad air with something else that smelled bad probably was sort of the idea, right? And again, thinking of ways we fumigate with sulfur, maybe, they were sort of onto something there, not for necessarily the right reasons. And this is my favorite here, burying a toad in a pot to prevent millet diseases. Okay, so of course, we need to fast forward with human medicine to individuals such as Pasteur and Koch and the germ theory of disease, who didn't necessarily come up with the idea, but they at least proved essentially and were able to convince the medical establishment that microbes could actually cause disease and were not just the result of disease. And then, of course, our own parallel here, Anton de Berry, who proved the microbial cause of late blighted potato, which really, of course, was the start of plant pathology as a modern discipline, when we actually finally realized that it was microbes that were leading to many of these infectious diseases. Before this time, of course, it was thought, for example, in the Irish potato famine, that these potatoes were simply absorbing too much water, right? That was the prevailing sort of popular theory. Okay. So just thinking of other class topics here, again, plague, famine, and beer, it's sort of divided into three different sections. The plague section is largely focused on human diseases. So I talk about things like the Neolithic Revolution, the advent of agriculture, and how that led to different types of disease pressures on humanity, the rise of cities and urban areas, and increased contact with domesticated animals, for example, bringing us new diseases which probably hunter-gatherers never had. Other types of things like biological warfare, the Columbian exchange of diseases between the old world and the new world, which led to a lot of really profound demographic changes. And it just, on the bottom there, teaching during COVID allowed some interesting conversations on the reaction of the government to COVID and to the reaction of government to the Spanish flu about 100 years ago. Famine is, of course, the plant pathology section, where we talk about the history of plant disease, and there's 4 diseases in particular I spent time on: wheat stem rust, Irish potato famine. Ergotism, of course, is a very colorful history and is very popular with the students. Chestnut blight, at least in North America, is a profoundly important ecological disease in the 1940s. And then some other interesting topics like fungal anthropology. Robert Blanchette, who brings forth all these artifacts that he has looked at in museums and different uses of fungi by Native Americans, for example. And beer, of course, which you might suggest is the reason I'm trying to draw some more students into the class with putting that in the name. This is the 3rd section. I'm also trying to say that microbes aren't all bad. There are good microbes. We shouldn't be too mean to them. So, of course, history of beer, wine, distilled alcohols, fermented foods, antibiotics, history of microbial biotechnology, things like that. Okay, so student goals, overall class goals for this course, of course, exposure to plant pathology. Most of these students, this is probably the only plant pathology course they will take, but who knows, maybe 20 years from now, they become important figures in government, are in charge of funding, so it's
Sorry, we
it's
are,
good for them to know.
you should go to the conclusion. We are close to the end of the time.
Okay, sorry about that. So practice doing the work of historians. So they have to look at primary sources directly. Just an example there, a letter from Leeuwenhoek to the Royal Society of London. More informed citizens, things like vaccine hesitancy, unfortunately, have become more of an issue after COVID. So telling the story of smallpox eradication is a very important one. And then just a great appreciation for the scientific process and the nature of inquiry. So just want to quickly thank some individuals here. A couple of former departments heads I've had who've been very encouraging and supportive of my development of the class, Carol Ishimaro, and also Jim Bradeen, who's sitting right there and has a podcast called Plantopia, if you're interested in it. And also Tracy Wilson, who's a U of M teaching specialist, who gave me some good advice on online teaching. Okay, thank you.
Do we have some questions for Brett? Have time? Yes. And feel free, I heard about the podcasts, feel free to post a link to that also so everyone can see.
Quick question on the approach. Is it learning-centered, student-centered? How have you designed your course?
Well, I try to pick subjects that are interesting to me. I know that's a selfish thing to say, but I find that when I talk about things that are interesting to me, I'm much more passionate about them, and I find that they're delivered better to the students. But instructor focus, is that a bad thing to say? Probably.
Okay. One quick question there, just behind you.
Thank you so much. It would be more of a comment than a question. Thank you for your lecture, because I was really amazed how, my slides, some of my slides, some of your slides look exactly like my slides and my lectures. So I would just like to, I'm Martina from the University of Zagreb in Croatia, so I teach basic microbiology courses as well as the specialized molecular plant pathology. But response of the students to things like that is always the same. I even sometimes give them a choice to read a book on Irish potato famine or a movie or things like that. And response is always great. They always love the things like that. So thank you so much.
Okay, thank you very much. So remember that you can also post questions in the chat for the speakers. Yes, the next speaker is James Stack from Kansas State University. And he is going to talk about graduate education in plant pathology from a perspective on how to prepare scholars to advance the area. You're welcome.
Yeah, thank you very much. So a little bit of backstory on this. It's Lodovica's fault. So Lodovica actually contacted the second author there, Jackie Fletcher, and invited her to write a paper on this subject. And Jackie was associated with the rest of us through a course I'll tell you about at the last slide or two of this presentation. And so that's how this really came to be, is there was a group of scientists from several different countries that I'll tell you about at the end, but we were all together when Jackie got the communication from Lodovica, And Jackie said, well, why don't we all do this together since we've been discussing this issue? So that's kind of the backstory on this, is that Lodovica invited us to contribute to a paper on this. So the paper is the basis of this talk for the most part, and it really kind of fed into this manuscript that I suggest you read if you want the whole story, because I'm only going to talk a little bit about it. So this presentation, I'm going to focus mostly on that first part, graduate education in plant pathology, but because of the focus of the session, I decided to insert a few things that we've heard about throughout this conference, and that's the concern about the awareness of the importance of plants and plant pathology just throughout society. So I'll throw in a couple slides on that. And then I'll just kind of round it out with the course I teach and just talk about the way I do that. So graduate education. Again, the authors of the paper, Jackie Fletcher, who is a emeritus distinguished university professor from Oklahoma State University, Abraham Gamliel from ARO, Volcani Institute in Israel, Maria Lodovica GULLINO, that you all know, Simon McCurdy, who is the director of the Harry Butler Institute at Murdoch University in Western Australia, and Grant Smith from the New Zealand Institute for Plant and Food Research in New Zealand. So it was that collective discussion that led to the comments. So I'm guessing most everybody's heard of flipped education, so this is going to be a flipped presentation. So normally I would give the talk, you would ask the questions, and then I would answer them. I'm going to ask the questions and hope to get answers from you. So this is the paper. I hope you pick it up, but one of the starting points for that was education is the foundation for progress in science and society. But what is the purpose of education? What is the purpose of a graduate education? Education and training, is there a difference? So training is learning to do something. It's acquiring a skill. Education, on the other hand, is increasing your knowledge and understanding such that you can advance that thinking, and it's the foundation for continued learning. So no, they're not the same thing. Purpose of a college education, well, in the United States, 70 years ago, the American Council on Education said it was institutions of higher education exist to educate students for lives of public service, to advance knowledge through research, and to develop leaders for various areas of the public service. So that was the attitude 70 years ago. But just not long ago, the attitude changed substantially. Today's universities are required to prepare graduates with the knowledge, skills, and ethical responsibility to meet the future workforce needs of society and to participate fully in the global economy. So if you just look at kind of the highlighted there, the shift is from education being about the betterment of that person such that they can contribute to society, to a shift that the purpose is to help that person get a job. And that's not the same thing. So a paper by Bustede, what is the purpose of college? College is about preparing a person for work. This is in 2019. To help them get a good or better job, and by far the most commonly cited reason why Americans value higher education. It's about getting a job. College is about more broadly preparing a person for success in life, to be engaged, enlightened citizen, capable of thinking critically. These are my highlights. And communicating clearly. Bustede claims it's a false dichotomy. It's really about all of that. A thought for the day, I don't know if Wordsmith, look it up. It's kind of a fun app to have. Every day you get a new word in the English language. It tells you the derivation of the word, where it came from. It's kind of fun, the definition. But they also have down at the bottom of the daily clip a thought for today, and it's a saying from somebody. The principal goal of education, this is Piaget, should be creating men and women who are capable of doing new things, not simply repeating what other generations have done. Men and women who are creative, inventive, and discoverers, who can be critical and verify and not accept everything they offered. So again, if we just kind of pull out a few critical elements there, it's not simply repeating what other generations have done, it's being creative, inventive, and discoverers. It's about intellectual development. Undergraduate versus graduate, this is my perspective. The primary focus of an undergraduate education is learning principles and assimilating facts. The corollary, the primary focus of a graduate education is to develop how you think about the facts and what you think about the principles. It's more about thinking and analysis than memorization. It's building on existing knowledge to generate new knowledge and deeper understanding. There are different perspectives on that, I recognize. Purpose of a graduate education: to learn and do research, become skilled in contemporary technologies, and to publish manuscripts, or to gain a deep understanding of subject matter in order to become a scholar that is prepared to advance that discipline. Are they the same thing? No. It's really a combination of all of that, but I fear we have lost sight of that second line. From that paper, over the last few decades, we've experienced a rapid expansion in knowledge, fueled in part by the rapid evolution of the technologies that underpin science. Growth in new disciplines and subdisciplines coincident with the rapid expansion in scientific journals over the same time period leads to important questions regarding the education of the next generation of plant pathologists. Specifically, what is enough for a student to know and to achieve in order to fulfill the requirements of a graduate degree? They can't know everything. Have we become too focused on the acquisition of technological skills at the expense of developing a broad and deep knowledge base essential to the advancement of plant pathology? Our goal should be to generate scholars to advance our discipline. The challenge is to determine the best way to achieve that goal. Should a PhD program require coursework or be solely focused on research? It is a research degree. Do research is the argument in support of no coursework. And that there are certain degree programs around the world where it's strictly a research degree with no course requirements. There's a consequence to that that we need to really think about, that, as illustrated in the earlier presentation, a lot of students come into plant pathology from a wide array of experience and disciplines. So what ties the discipline together if they're not brought into the general body of literature? Is the decline in taxon-based courses a result of careful deliberation as to the best approach to graduate education, or a consequence of the fragmentation of the discipline? The increase in knowledge in all areas of science affords the opportunity for deeper understanding, but is it at the expense of breadth of knowledge? Education is the foundation, but there's an important relationship between science and technology, and that relationship impacts education. Historically, we would develop a question. We would develop a hypothesis from that question. And we would choose the technology that allowed us to address that question, whether it is utilizing existing technology, or maybe it led to the demand to develop new technology. Hopefully, it derived a solution that led to new knowledge. And that knowledge allowed us to ask a new question. That is the basis of science, or was. Creativity, develop hypotheses and new technologies. The innovation was the application of those technologies to derive solutions. Historically, there was a balanced push-pull relationship between science and technology that led to progress, driven in large part by the scientific questions being asked. How has technology impacted our science? We ask new questions about the pathogens that threaten plant health. What is the core, accessory, and pangenome? We would not have asked that question when I was in graduate school. Which genes are upregulated during infection? We ask old questions in new ways. What are the mechanisms by which pathogens communicate with their hosts? How are some pathogens so variable? We asked those questions 30 years ago, but we're getting different answers now as a function of technology. Increase the depth of our understanding of the nature of plant diseases and the pathogens associated with plant disease. Technologies influence how we fund research. There are grant programs focused on technologies. NGS, genomics, drones, bioinformatics, computing, AI. I question whether that's healthy for science in the long run. Technologies influence our curricula. Courses built around the technologies, bioinformatics, biotechnology, computing? Is that at the expense of the traditional disciplinary courses? And is that okay? Today, if we look at this, it's reasonable to conclude, maybe unjustly, but I'm okay with that. The technology has assumed a larger role in that push-pull relationship. Is technology determining the questions asked? Whereas we see a grant program in data analytics. Now, we don't care what you analyze as long as you're developing this technology called data analytics. And that applies to many technologies. Rather than the science determining the technologies employed, is technology disproportionately driving the science? And I think it has been for a while. Have we become too enamored with technology? We do things because we can, not necessarily because we gave it thought and decided it was a good idea. One example, citizen science. I was at a meeting and a scientist was explaining this new program they had with citizen science involving them in geocaching. Everybody knows what that is, so you have a bunch of sites and you encourage people to go check out that site, you get a marker and you go to the next site. Well, doing it with invasive species. So I'm sitting here thinking, is that really a good idea that you're encouraging people to go to each of these sites with invasive species? Are you not concerned you're going to encourage spreading them around? Do technologies predetermine the science questions we ask? And then again, the funding programs. Challenges for graduate education. There are very few undergraduate programs in plant pathology, certainly in the United States. So again, our students come from a wide array of backgrounds. If we are not offering curricula that bring them up to speed on the science, are we further fragmenting our discipline? Currently, with respect to graduate classes in plant pathology, students often start at different starting points. That's a challenge for us. Should a graduate degree program require coursework? That's a conversation going on in my department, a historically really strong plant pathology department in the Great Plains region, and we have a few faculty that have adopted the thing. This is a research degree that we don't need to do coursework. Fortunately, it's not a prevalent idea in the department yet. What courses should we require or recommend? Again, we're adding courses constantly, sometimes as clear function of the technology development. Should core taxon courses require lab sections? In order to accommodate all these new courses, some of our core courses are giving up lab sections to fit in new topics. How much is enough for a degree in plant pathology? That is a discussion we need to have. Highly skilled technicians to execute the research agenda, or highly educated scholars to advance the discipline? It seems like we're at that point, but we need to find a compromise that allows us to move forward with both. Scientific literature. Do you go to the library to explore literature? Or do you get your literature online? This is where technology has had a major impact on me. So a long time ago, yes, I'm that old, before online searching, I used to dedicate a half day a week to go to the library, read the new issues of the journals, browse the ones I didn't know anything about just to see what was going on in the world around me, and then hit the stacks. I don't do that anymore because I can search from my office. The consequence of that is you only see what you're looking for. That's not good for science. Is the older literature relevant in today's science? Because again, if you're only online, you're not going back very far. Have you read the Phytopath classics? Does everybody even know what they are? So here's a few of them. From the first two from the 1700s, attempt at a dissertation on the diseases of plants. And I think Brett drew our attention to this a few minutes ago. Dissertation on the cause of the corruption and smutting of the kernels of wheat in the head, on the means of preventing these untoward circumstances. So these are Phytopath classics. They are available from APS Press. I'm not trying to sell anybody these, but why would you want to read these? Well, because they provide excellent examples of the importance of critical thinking to scientific progress. These people were actually brilliant when you sit down. Did they get it wrong? Yes, of course they did sometimes. But here's a great quote, I wish I remembered who to attribute it to, that I get. The difference between a scientist and a philosopher is that a scientist would rather execute the definitive experiment that shut down all further research in that area, whereas the philosopher would rather be so spectacularly wrong that people talk about it for a century. And then there's historical context that's important to the discipline, again, as Brett drew attention to. Observations, Botanical and Physiological on the Potato Murrain by Berkeley. He's one of the founders of our science. Isn't it worth reading that classic? Questions to consider. Do we often decide on the solution before the problem has been adequately described? The answer is yes, in my opinion. Nanoscience will solve all your research challenges. I was in a discussion recently and a scientist told me that before we ever described what I worked on. Is the steady decline in the number of plant pathology departments an indication of the evolution of our discipline through integration into other disciplines or a reflection of the fragmentation to more specialized areas? I'm not sure yet. Subsuming plant pathology into very broad areas like biosecurity or merging the departments into multidisciplinary units may obscure or remove the disciplinary context essential to advance the discipline. Is the discipline of plant pathology on the road to extinction? Do we need a discipline of plant pathology? I think we need to be making the case for that. So that's the end of that part. Raising awareness of plants. Now, I do this a lot, and have been for a long time because of the nature of the position I have. So over 100 million people visit botanical gardens every year. Every major grocery store and department store in the United States sells ornamental and landscape plants, and that's true in many countries. Urban and community gardens are increasing dramatically. People haven't lost their connection to plants, they've lost their awareness of their connection to plants. We need to remind them of that connection. We need to point out the consequences of not protecting plant systems. Their life depends on plant health. That's the point we need to make. Not that they need to understand plant pathology, they need to understand the consequence of it not existing. In the United States, President Biden signed a new national security memorandum on November 10th in the last fall, calling for enhanced preparedness for biological threats, and importantly, they've now included natural and accidental along with the intentional, thanks to SARS-CoV-2. But importantly in that document and all the related documents, it calls for a more inclusive One Health concept that recognizes plant health. This is a first for us. So the new definition, I'm not going to read this to you, expect you to memorize it, but importantly, if you look, the new definition of One Health in the United States has pulled plants out of the environment component, so it now reads people, animals, plants, and the environment. That's a big step.
James, sorry, 2 minutes.
No worries. We should take advantage of this One Health window that has been opened. Why do I say that, and why does that matter? It's way past just that plants are important for our nutrition. There are very direct relationships, and there are very strong evidence for why plants need to be in that One Health concept. The World Health Organization last October released their fungal priority pathogens list. I'm not going to go through this, but bottom line is this. Over 150 million severe fungal infections annually, 1.7 million deaths. That's more than dying from malaria now, from fungal infections. And guess what? Some of them are plant pathogens. We're seeing a dramatic increase in multi-fungicide-resistant pathogens of plants that are causing disease in humans. Rhizopus caused a disease in maize in humans, and it was isolated from the wooden tongue depressors. That was the direct delivery. Global warming will bring new fungal diseases for mammals. This was published, two people from Public Health published this in 2010, but it's coming true. India man, world's first person to contract fungal infection from a plant. This is Chondrosterum, first infection in humans. Agricultural origin of resistance for Aspergillus fumigatus, one of the most serious pulmonary infections in humans. The fungicide resistance directly linked to agriculture. Plants as alternative hosts for salmonella, and it goes on, E. coli, listeria. These are bona fide plant pathogens. It's not surface contamination. These are bona fide plant pathogens. So raising awareness, we need to take advantage of the One Health window that has opened. We need to remind people of their connection to plants. We need to point out the consequences of not protecting plant systems. Ways of teaching plant pathology, there's just 2 slides here. Education doesn't end with a degree. We need career-long, lifelong education. We need to provide professional development opportunities because of the changing landscape of plant diseases, rapidly expanding knowledge base, evolving technologies to underpin. So I teach a course. This is a professional development opportunity. It's a 1-week intensive course in our biocontainment facility at Kansas State University. It's called Plant Biosecurity in Theory and Practice. They receive training by a professional biosafety staff. They actually get to play. Boy, I would be disciplined for saying that. They get to work, real experience in a biosafety level 3 biocontainment lab. They organize in teams. Each team is a country, and they have to develop biosecurity plans to protect that country's plant resources. We do a half-day forensic desktop exercise to help them think in a completely different context about how to approach an agricultural system. Biosecurity case studies from around the world to raise their awareness of what's happening. And then social networking opportunities and a hike in a native prairie ecosystem. My co-instructors, each year between 4 and 6 from different countries. Participants so far from over 25 countries in the last 7 years. Graduate students to seasoned professionals. So it's a very, very good mix. And it's a total immersion experience. So we talked about graduate education, raising awareness of plants and plant pathology, and ways of teaching plant pathology. Thank you very much.
There's room for a whole discussion there, I think, but we have time for 1 or 2 questions.
I be cheeky and ask, who of you here consider yourselves plant pathologists? Who considers themselves plant pathologists?
Yeah, thanks.
Okay, keep your hand raised if you did an undergraduate degree in plant pathology. Keep your hand raised if you did an undergraduate degree in plant pathology.
Yeah, I'm going to brag here. I was fortunate that George Agrios was my undergraduate advisor.
Okay.
So we were talking about should we have, I don't need to stand, but should we have a discipline of plant pathology? Most of the people that have that consider themselves plant pathologists don't have undergraduate in plant pathology, and this is something I'd like to research. So, can you define an undergraduate? Like master? Undergraduate is there's no, it's no, not high school. Bachelor's, a bachelor's, yeah.
There are no bachelors in Sweden in plant pathology.
No.
Not really fair.
Is that it?
That was it. I just wanted to do a quick survey because it's interesting.
Okay.
Thank you very much.
Thanks. Introduce the next speaker.
So we will move to the next speaker, Demetrio MARCIANÒ. And so it will be a step forward in the application and teaching of modern statistics in plant pathology.
Okay. Good evening, everyone. I'm Demetrio MARCIANÒ, and I'm a PhD candidate at University of Milan. And this presentation is mostly based on my personal experience as a student during the second geological era, and from teaching and tutoring activities I've been involved in during the third geological era. So, sketching the plant pathologist identikit, we can say we have a strong background in life sciences. We work at different scales, from the lab to the field, and we are usually interested in the evaluation of the plant pathogen interaction. In a survey from different employers, from academia, government, and private sector, which was done in 2009, we can see that the ability to employ statistical analysis is quite researched by the employers, and it's even higher in some cases compared to the experience in diagnosis and also the knowledge of plant disease control itself. So why statistics is so important in our field? It's important because the plant pathogen interaction is a complex phenomenon which is affected by many factors, and this fact dramatically increase the variability associated with our experiments. Therefore, the use of appropriate analysis is essential for the successful exploitation of data, avoiding misinterpretation, which is a waste of resources. So the relationship between our disease responses and multiple predictor variable is a common situation in our field. And since we are in the big data era, the ability to handle large data sets such as those coming from omics sciences and to relate them to our variables increase the needing of multivariate statistics. So we are always interested in two main variables, which are disease incidence and disease severity, and I think that most of you in this room know them very well. And usually we always employ, since by looking at the literature, we always employ two kind of analysis, which are one-way ANOVA and linear regression. But if we look at the assumption they have, we notice that plant pathology experiments often involve incompatible response variables, and also they are not suitable for our situations like factorial design and repeated measures. So what I noticed from my experience is that to meet assumptions, usually data are transformed, forcing the use of model developed for other purposes rather than using appropriate statistical model. And I also noticed that my students and also some researchers often ignore data nature and force the use of traditional techniques they are comfortable with. So these usually lead to a blind search for significant p-values and thoughtless use of post-hoc tests, which are then reduced to letters or asterisks, which are pretty meaningless. So if we also consider that ANOVA is just a particular case of regression, very often for us is just a matter of regression. So why don't we adapt our regressions to the empirical distribution we observe from data, and we exploit the prediction given from this model for a straightforward interpretation of the results? So I think that we should change the way we teach regression to our students. And I think that we should move in two steps. In the first steps, we should teach them how to critically evaluate the data to determine the appropriate model family that suit them better, like linear, generalized linear models, beta regression, adaptive models, mixed models. And in the second part, we should evaluate the results coming from this model, which sometimes is tricky, in particular with more complex models, finding a way to exploit the prediction for analyzing the inference we observe in data. So I have a very simple example for you. We have this data set composing from a response variable, which is disease severity expressed as percentage, and 4 factors, which are different strategies used for crop protection. So if we look at the data, if we look at the violin plots and the kernel density estimation, we can clearly see that those data are not normal, and they may be heteroscedastic, so they are not suitable for linear regression. So since we have a tool designed for handling proportion and percentage, why don't we use them? We use it. And for this reason, I would go with a beta regression model, which handle these data in their original scales. And it also can account for over-dispensation in data. And as you can see, it can also adapt to a wide range of situations. You can see the curve moving. That is the range of distribution we can adapt the beta regression model to. So once we have a regression, we need a clear way to make inference on results. And for this reason, our colleagues from the clinical sciences often use this tool, which is called estimated marginal means. These are used a comparison tool and are descriptors obtained from a regression model. So we use the model to estimate our variable. And in this way, we can express it with the same unit and with the same nature. For instance, in this case, we are evaluating disease severity means. So we are getting means. If it was a logistic regression, we would have estimated marginal means referring to probabilities. And they also displaying uncertainty as confidence or credible interval. And here you can see how they look like. I place them sided to the box plots, which show the original data and the estimated data from the model. And also here in the table, you can clearly compare what are the original data and those retrieved from the model. In this way, we can have a straightforward interpretation, which is easier than random asterisks and letters on a graph. Moreover, these tools also adjust the response variable to the factor level and also compensate for the imbalance in the data, such as that one coming from the presence of outliers. These tools are very well supported by open source statistical tools since the community provides valuable tools to peers based on their experience and especially needs. But I've noticed from my student that the implementation can be difficult for inexperienced users and it can cause frustration and also a steeper learning curve. And that's why. Because even plant pathologists are skilled profiles, they're not computer scientists. So they may lack programming skills. So to overcome this issue, I started to use this tool for my students. And I found that these collaboratory notebooks are a good way and a convenient solution for all of us, even researchers, students, and teachers, dealing with coding issues. These notebooks are platforms that allows users to write, edit, and run open source code, like those written in Python and R, on remote servers, using advanced computing resources, also supporting GPUs and TPUs, which is very important in the last years for the advance of machine learning, and especially deep learning. And in this way, by integrating different programming languages, since R is better for statistics and Python is better for machine learning, we can also join both basic analysis, such as ANOVA, and also advanced analysis, such as machine learning, in a unique environment. And also, we can provide the users a free and direct access to this tool with a plug-and-play approach. Indeed, both students and researchers can run analysis autonomously, and no programming skills are required. Indeed, the code is accompanied with a description for those who want to learn how to code. But in the end, for those who never use this tool, it works just like this. You have to press a button and the analysis is done. So take-home messages from my presentation are that plant pathology involves complex experiments and several variable types. So I believe that teachers must increase consciousness on appropriate tools for that analysis, and they also have to provide these skills to their students. And also, I think that open source and collaborative tools can provide in the future a common benchmark for teachers and researchers to facilitate the reproducibility of the analysis and also to support teaching activities. And in this way, we can focus the attention on that analysis rather than on other issues like coding. So that's, I turn to you because I have an idea, but I need some support. So I would like to generate a repository containing collaboratory notebooks suitable for plant pathologists, providing examples from published data and ranging a variety of potential useful situations for people working in our field. So I will start to upload something. It's ready after my PhD thesis will be done. So if you would like to collaborate, please get in touch with me, and thank you for the attention.
Thank you a lot. We have time for a few questions.
I don't know if I can formulate this as a question, but it's maybe more of a remark. As a statistician myself, I totally agree with you with 2 points. First one is that plant pathology generates heavily complex and huge data. And the second one is that plant pathologists are not trained as a statisticians or data analysts in the first place. So I definitely agree with you with the fact that better statistical education is needed for plant pathologists, but there is a limit up to which a plant pathologist will learn certain things, because statistics is a discipline by itself, so there are many, many things that even statisticians do not know, so it's a continuous education and learning. So my suggestion as a personal experience as a statistician working with plant pathology is try to get good statistician and good data analysts in your labs, because you're gonna need them. And if possible, when you do experiment, ask them before doing the experiment, because coming with a pen drive and asking do the magic, most of the time it's too late. So ask is a stupid way of while thinking about your experimental design before, and get in touch with experienced statisticians that they are the master of experimental design, because is the best way of keeping track from the beginning to the end on how your data are handled and analyzed and how you want to show your results. So it's not more of a question, but it's a remark in support of what you say. Thanks.
Thank you for the talk. This is to add to the point already said, but as a student, I had some statistics courses, but then we had these basic methods that you mentioned in the beginning, and then I was wondering, how much a student, if we're talking about teaching, how much a student is expected to, if his major is in biology or whatever else, also have these statistics, because then it's 2 majors instead of 1, and I was wondering, like you said, that we have to educate people about how to use the right models, but then they also have to understand the math behind it, and then are we studying math, because and how to choose. So this is just to add on a point. I'm not sure if there are thoughts on this as well, or how that would be embedded in the curriculums of students, if that would, because I feel like I'm working on my thesis and I just feel overloaded with data, and now I've learned that I'm going to analyze it wrong, but I will have to write it anyways if I want to have my thesis, so in the end I'll just have to accept that my data are frauded in a way.
I think that the main core of my talk is about raising awareness about the existence of other tools. Then, of course, we should ask the more experienced people, which is the better option. But I think that also providing some tools to play with can also increase the confidence and data handling for students who also might want to work outside academia and so on.
Does someone else want to ask something? Let them ask first. Teaching and learning.
Well, go ahead.
I can give a personal experience. So during my PhD, I had to try and do some stats, and it was just a mess because I couldn't trace anything. And I started to use R, and I had a lot more confidence because I could see why I was doing things and why was it working, why is it not. But the core for me was actually who taught me and how they approached it. I was originally trained by a mathematician, and it was really difficult. It made me feel really stupid. I was like, but I'm a plant pathologist, I'll never get this right. And I went to visit Emerson Del Ponce's lab, and they were like, hey, you can do this. Here are the right tools. Here are the right people. And just the right approach, I started to get more confident, and it'll be fine. You have to, that's also what a PhD is about. It's about learning what to do and what not to do.
And we will move to the next speaker, but before I will do some advertisement for French people only. So I have the same opinions as you. So we are doing a workshop in December for plant pathologists, but more for researchers, because we need to raise awareness about which statistics they should ask their students to use, because it's too late for us. So you should come in Montpellier, December 14th. We will talk about which statistic to use with multivariate analysis to identify factors that will explain the efficiency of biocontrol or biostimulants.
Yeah, I just add one thing for those who feel depressed. My worst grade during my academia career was statistics.
So with those encouraging words, we move to the last speaker, as comes from Université de Lorraine. It's Benjamin Peter. Sorry for my pronunciation.
Okay. Can you hear me at the back? You hear me? Yeah? Okay, good evening, everyone. I would like to thank Elsa and Erik first for putting together this nice session. And I perfectly realize my talk is the last thing standing between you and a fresh beer. So I will try to be as quick and clear as possible. So I would like to start by the problem I would like to address in my talk, and James actually put it very nicely for me. He said in the digital age, students are hyper-focused because they find only the papers they are looking for, which means that they basically miss the broad conceptual understanding of the field, that they need to be creative and to prepare dissertation thesis, for instance. And actually what the students struggle with is to find papers to analyze out of the thousands that are published each year, and also to find a way to analyze them in a way that is meaningful, so they could extract information that they could use for their work. And so the objective of the project I present today was to design an easy-to-use and focused method to perform literature reviews. And I really designed this method with a PhD student in mind, a PhD student who could perform this, use this method at the beginning of the PhD. So the two steps, I don't know if you see my, yeah. The two steps of this method is first to find influential publication in a given field, and secondly to analyze them in a data-driven manner. I say analyze and not read, because it's really about analyzing data and getting information out of the paper. And then I will try to analyze by asking three questions that I try to answer. And this is the outline of my talk. So first, I tested this method in a field of molecular plant immunity. This is a field I'm familiar with. And so I've been looking for highly influential publication in molecular plant immunity, HIPPIes. So I will say hippie a lot in this talk. I'm not referring to drug users, just scientific publication. Okay. And what I mean by highly influential, it's not published in high impact factor journals, not at all. I mean highly cited papers. Citation, it's an article-based metric. It informs quite well on the influence of this manuscript or paper. And it's a useful way to find the classic papers in a given field, because they are really highly cited. I just mentioned here what I consider influential is not quality. So I'm not claiming that the cited papers are good quality papers, they are just influential. So basically, to make it quick, I use the Web of Science engine to search for highly cited papers published over the last 20 years in plant immunity. And I search for research articles and reviews. And I use a combination of three different keywords: plant immunity, plant defense, and plant pathogen, to capture a bunch of articles that are extremely highly cited in the field. As I said, these are the classic. And just to give you a glimpse of how they look, the HIPPIes is 170 papers. There are actually only 0.2% of all the papers published in this field. but they represent more than 4% of the citations. So they are really the tip of the iceberg, if you prefer. And if you look on the right-hand side, you see all the papers covering nicely the last 20 years of research. You see the review articles and research articles. And just to mention the most cited paper of all that receives the most annual citation rate, it's the zigzag model published by Jones and Dangle in 2006. Just out of curiosity, raise your hand if you have read this paper. Okay, so it's really a classic in our field. And as a note before I continue, I just, out of curiosity again, I looked at the correlation between the citation received by these papers and the impact factor of the journals. And as you can see, there is nearly no correlation between the two. Actually, most of the HIPPs collected, they were published in journals, disciplinary journals with impact factors sometimes lower than 5. So with that in mind, I've tried to analyze these papers to answer 3 questions. The first one is, what are the main research questions addressed by the HIPPs? And to do so, I had to spend 3 weeks just basically reading the paper. So going through the abstract, the title, and the paper, and try to assign keywords to each paper to kind of do it iteratively to assign categories, to put the papers in different categories. And this is the result of the process. I won't go through everything, it's not the point of the talk today. But basically, I hope you agree with me, if you do this kind of exercise, you end up having first a figure for your thesis introduction, but you also develop a very good analytical understanding of your field. You are very familiar with the research questions, the body of knowledge created addressing each of these questions. Second question was, what are the main model objects? So by model objects, I mean organism, so model species, but also model molecule, because we are in molecular plant immunity. And so to answer this question, we perform text analysis. So we collected all the title and abstracts of the paper, aggregated them together in a single text file, and that was nearly the size of a Harry Potter book, 30,000 words. And then we just remove all the words that do not explicitly refer to an organism or a molecule. So results, novel, method, findings, etc. And we ended up with this word cloud where every word, the size of every word reflects the frequency of the word in the title and abstract, and every word explicitly refers to a molecule or an organism. And again, without going in the details, this kind of word cloud is a very good starting point for students to make sure they are familiar with all the key objects in their field. And if you went to some talks this morning, if you don't know what FLS2 or ROS or EFTU means, you probably didn't understand the session at all. So it's a good starting point for students to make sure they understand the jargon of their field. And just to go a bit further about this, I cannot resist just to show you the quantitative data here. Actually, most of the EPs, they addressed only one plant, which is Arabidopsis, and very few EPs went on cereals and tomato or potato. And on the other side, most of the plant-associated organisms studied are actually bacteria, most of the time. So this just tells us that most of what we know of molecular plant immunity actually derives from a single interaction between a plant and bacteria, most often Pseudomonas. And last question, who published the papers? So this is not about the science, it's really about the research community behind the science. So for this, I first look at all the corresponding authors of the HIPPs, and I first try to put them on a map, to look at the countries they are from and the cities they are from. And what you see basically here are all the countries with colors. They are countries in which you can find corresponding authors, so where the labs are actually based. And I think the message here is that most of the labs actually come from the US or North America, Western Europe, China, Japan, and Australia. So a very limited number of countries actually. And if you look in these countries, most of the time you see that the labs actually coalesce or group into specific cities where there is a very strong culture of plant pathology research. The big dots here indicate that you have more than 5 labs publishing HIPPs in these cities. So this is kind of informative for students and postdocs when they are looking for jobs, because these dots actually tell you where there is a very strong culture of research in plant pathology, which means job opportunities and probably very good training and mentoring environment. And just to put numbers on the map I just showed, I quantified here a couple of indicators, and actually only 6 countries contributed 80% of the EPs, US being the first by far. Only 6 institutions contributed a quarter of the EPs, and we heard a lot about the Sainsbury Lab or the Max Planck over the last days. These are very strong institutions when it comes to molecular plant immunity. And finally, when you look at the journals, 6 journals contributed 50% of the EPs. And the fact that we see nature and science here just tell us that as a field we are quite visible for generalist biologists or scientists. So it's an indicator of the healthiness of the field, I think. With that, just 2 take-home messages. The first one, so the EPs address coherent research questions and objects and are shared by a very small structured research community. This is what I've just showed. And about the method, so we call it the HIP-in method. It means a highly influential paper in whatever the field you want to study. It allows to easily snapshot research fields. So in other way, you can easily take a photography of a research field and get information from it. And I say easily here because it doesn't require any skills related to data analysis or R or any software. You can just do it knowing how Excel works, basically. So everything I presented is in this paper, the HIP paper, we call it. It's in MPMI, so I encourage you to read it if you want more information. And you can also look for the Louet et al. Paper. It's a sister study that a PhD student in our lab did, focused only on effector biology. And if I have 1 minute just to conclude quickly, so I was quite proud with this study, and I presented it to my master student this year, and they basically come back with a critique. They say, we are interested in France, actually. I'm teaching in France, and they want to do internship and PhD in France most of the time, so they don't care that most of the labs are in Germany or Japan. So they ask me, can you just apply this HIP-in method by focusing on France? So that's what I am doing at the moment. I'm just resurveying all the papers published in France over the last 20 years and trying to use this collection of papers to redo the same analysis. And so far, this is just what I did. It's a glimpse of what I'm doing. I use this data to make on the map all the labs in France that have published papers over the last 20 years in our field. And of course, I will soon associate with all these labs information regarding the models and the research questions. The idea being that I could provide students with this as a directory to help them find their way in the different labs and topics they want to pursue in their career. And I think Lodovica mentioned at the beginning that it's critical to attract students in our field. And I think this is one way to do it, to help them understand and see what are the job opportunities and encourage them to join our community. Just to finish, so I would like to thank my colleagues Clémentine Louet, Julie Lins, and Sébastien Duplessis. They are my co-authors on the study, and also other people in our lab and collaborators outside who were kind enough to critically read the manuscript before we sent it for publication. I have no funder to acknowledge because this was a COVID project, so it's a completely side project that I performed in my bedroom, to be crude. And I thank you for your attention.
Thank you. That was really exciting. I have 2 quick questions. One, first of all, a paper that was published 6 months ago could be the most profoundly important paper in our field, but wouldn't have been around long enough to garner citations. Is there any way to correct for that in your analyses?
Probably not, I would say. No, I don't see. Citation is an indicator of success over, you need to have 1 or 2 years to pass before you get the citations. There are alt metrics, so you can look on Twitter for the kind of the buzz, of course, when there is a big thing coming out. But I didn't implement this in the pipeline.
Yeah. I'm not sure there's a way to fix it. I just was curious what your thoughts were. The other thing I noticed, you mentioned that impact factor didn't seem to correlate well, but you also showed statistics that a lot of the papers came from Nature and Science and PNAS. Those seem to be at odds.
No, actually, you get some papers from Nature, Science, Cell, etc., of course, but you also get a lot of papers not from GLAM magazines. And you don't see correlation between these impact factors and the citation rate, basically. So I'm not saying that all the papers are from low impact factor journals. It's just that low impact factor journals can have highly cited papers in them.
Thank you.
So what model did you use to study the correlation?
Oh, sorry, I didn't check the normal distribution. I did linear regression a bit stupidly.
Just in response to the gentleman's question, I think you could include real-time data of how many times somebody's downloaded an article as a possible way to correct for that.
I didn't get the question, sorry, can you repeat?
Use real-time download statistics in order to correct for more recent papers that are still impactful.
Yeah, so actually, yes, you can, of course, look at the downloads and the views. The thing is, this is not implemented in the Web of Science. So you would have to rely on each journal website to collect this information. And also this information could be tweaked by people being very influential on Twitter, for instance, advertising their work heavily. So I don't know if this is a reliable information indicator of influence, actually.
Any more questions? We in the beginning. Yes, question.
Not really a question, but I think we did not speak about ChatGPT.
No, I was also a bit surprised that was not mentioned so far. Very good when you are very poor scripter in R, not mentioning any names, to get some help. I found. Any other comments on large language models or? Yeah.
As a statistician, I get requests from many different fields of plant pathology in which I know nothing. Yeah. Sometimes it's fungi, sometimes bacteria, sometimes interaction. And for me, it's a good way to start digging in without. I think what has just been presented on going through the most influential literature, but anyways, it takes a lot of time. Even when you identify those papers, you definitely need to read them. So asking ChatGPT to say, what is important when I'm looking for apricot canker caused by cellulose, and it gives you a lot of good ideas on what you have to look for. Say, temperature is there, rainfall is not, so you know things that you have to look for. So I use it, I don't type.
And the question I have is, do we need to deal with and to talk students about that and show them how to use it? And when I said how, it's with being fair and so on.
So I teach no, it's not it's a bachelor's in agriculture, but it's for those students in South Africa that are going to become, it's not the type of extension officer that you get in America. So it's usually people that they're definitely not going to do anything science-based, if I can put it that way. So I recently there's two things that I've seen about ChatGPT. The first thing is students don't know how to find information because they have information overload. So students need to be taught how to find relevant and meaningful. So relevant and meaningful is something that most of my undergraduates, some postgraduates, can also struggle with. So that's the first thing. The second thing is they might use it anyway, and that's where you kind of hope that you've been teaching ethics and integrity, so that if they know how to find relevant and meaningful information and they have scientific integrity, they will be able to hopefully merge the two and you either use the tool meaningfully or use it to brainstorm and leave it at that. That's just my opinion and from my experience.
Thanks answer that comment. We don't want to keep anyone from a beer, wine, or a cold drink. But as you might have seen, we had in the beginning these questions up as well. So, I mean, if anyone wants to stay on the room and discuss these, they were triggered, they are welcome to, and we will stay here, right? They were actually triggered that one of the speakers, invited speakers, were not able to make it in the end. Dawn Sanders from University of Gothenburg couldn't come to the meeting, and she has done a lot of writing on plant blindness that we were also thinking of putting into the mix here. But she left us with 3 questions, and they're quite for me, advanced questions. So I think feel free to have a look at them. I think the first 3 questions are maybe a little bit more easier, and we have maybe touched upon them. But her questions there on how might story-based scientific narratives raise plant awareness in a didactical situation, how can that help? How can we involve artists in I think her background was here, avoiding plant blindness, are interesting questions. So feel free to stay on in the room and keep the discussion going. If not, thank you so much for being here.